Welcome back to the course of Process Control. Let us continue our discussion about model development for process control system design. We have many types of models. In this session, we will only focus on development of fundamental models. Our goal here is models that can describe the phenomena in a chemical process. But where do we start? A lot of processes in chemical plants can be modeled by using mass or energy balance. Let's review our model development previously. We always begin with the conservation principle, which states that accumulation equals input subtract with output added with generation or subtracted consumption. Take the total mass balance of a process as an example. We will get that mass accumulated in the unit operation corresponding to the process equals to total mass entering the unit subtract with total exiting mass. No consumption or generation, because mass cannot be consumed or generated under normal chemical processes. In dynamic model, we will get that accumulation rate equals to total entering mass rate subtract with total exiting mass rate. We can expand our model to detail all entering and exiting mass. Our previous model can describe the mass balance in the unit operation for the related process, but it is still irrelevant for real application. If we inspect our model here, we will see that the variables involved in this model, the mass accumulation rate and mass rate entering and exiting the unit, are usually not measured in real process. Instead, they are represented by other more measurable variables. In our example here, accumulation of mass in the unit can be represented by volume for gases or height for liquids. Of course, we need to adjust the representing parameter further. Take a process involving gases exclusively. The cumulative mass will be density multiplied with volume, and mass accumulation rate will equal to changes of density multiplied by volume over time, or in mathematical form, derivative of density times volume with respect to time. Other terms can also be converted to get this form of equation. Now we can solve this equation by observing the real condition of the process. Looking at our previous example, we can summarize steps of deriving the model for a process as follows. First, we choose the appropriate fundamental quantity for the control parameter. If we want to control liquid height, for example, we go for mass. If we want to control temperature, we go for energy, and so on. Then we define the control volume and apply appropriate assumptions for the control volume. Afterwards, we apply conservative principle for the quantity within control volume. We then substitute each term with measured variables and known parameters. Finally, we simplify them using various assumptions. This is our final model expressed in the state space form. Let's return to our stirred tank heater example. If we wish to control the temperature, the most suitable fundamental quantity for our parameter will be total energy. The control volume would be the entire tank, and we can assume that temperature in the tank is uniform. We construct the conservative law for energy. Substitute each term. Then we simplify the expression based on our assumptions. Sometimes we need additional physical or chemical equations to complete our modeling. Aside from using mass balance, we can also incorporate transport phenomena, kinetics, and thermodynamics equations. For example, heat transport, reaction kinetics, and phase equilibrium. We can also consider delays in our processes. Take liquid flow in this pipe as an example. If a temperature change occurred at time zero at the entrance, the exit will not experience change until later time. We can also use model equations to provide a constraining relationship. An example of them would be the outlet flow rate of a tank, which can be modeled based on liquid height. Let's look at another example. Say we want to describe the reactant concentration in CSTR. Our fundamental quantity will be mass of reactant. The control volume would be the entire tank, and we can assume that concentration in the tank is uniform. We construct the conservative law for reactant mass. Substitute each term. And then we simplify the expression based on our assumptions. Here we assume the volume is constant and the reaction is isothermal and first order to A. Let's continue our previous example, and we need to control the temperature in CSTR. Our fundamental quantity will be energy. The control volume will be the entire tank, and we can assume that temperature in the tank is uniform. We construct the conservative law for energy. Substitute each term, like our previous example for energy balance. Simplify the expression based on our assumptions. Again, we assume the volume, density, and heat capacity are constant. We add more equations, such as the heat transport and reaction kinetics. We take a reaction which is first order to A. This is the end of our session today. See you again on next session.